Hello everyone, this is Mr. Santos with another video video that I will be presenting today, and today's topic is about input-output ports on the AVR microcontroller. Alright, before I begin, a word to anyone who might be watching this video and to remind you that the videos in this series are targeted specifically for students at the University of Nebraska, particularly those who are taking microcontroller applications for our course, which is now called ECEN 1060. So please know that there are certain things, particularly when I talk about demos, that when we create projects, we do two project solution that you might say to yourself, well, what's this guy doing? This is kind of weird. We have a reason why we have to do this, so just bear that in mind. Other than that, there might be something useful for the rest of you, and but the primary target are our students. Okay, topics we're going to be covering in this video. I'm going to try to go as fast as I can. And that is, we're going to talk about the I/O ports in general. We're going to talk about the registers that you have to program in order to configure and use the I/O ports. We're going to talk about how to manipulate the I/O ports using the in and out instructions. We're going to talk about how to do bit level, bit by bit manipulation of the pins of the I/O ports. We're going to talk about how to do conditional instructions that allow us to test to perform certain instructions based on whether an I/O bit is set or cleared. So these are conditional test functions on I/O ports, and then I will give you a demonstration in do a quick simulation in the video so that you could see how this works with the simulator. Okay, so let's just go ahead and jump to it. Alright, right here on the screen you should be seeing a diagram, a very basic diagram of an AVR microcontroller for 8-bit architecture. Alright, and this is generic, but it's usually very similar for many of the microcontrollers provided by Atmel. Alright, in this example we have a microcontroller with 4 I/O ports. So each of these are I/O ports. Okay, and basically an I/O port is a window to the physical world. Is the interface by which the microcontroller can control some physical device. Okay, so for example, each I/O port has 8 pins. They're typically groups in groups of 8 bits, and each pin emits a voltage level of 0 volts or to 3.3 volts or 5 volts, depending on the logic level of the device. And then you use that to control a device. So for example, we can attach to this pin an LED, for example, that lights up whenever pin 1 is turned on, and it turns off whenever pin 1 goes to 0, assuming that it's wired this way. We could have another pin control a motor, say, and I'm oversimplifying just to get the point across. Usually there is some interfacing circuit that would be necessary to interface this digital device to an analog device such as a motor, but I'm just trying to get the point across. Okay, we could, for example, have a push button that is active low. So for example, when the push button is open, this would be pull high. Right? Say we have 3.3 volts here. So when the button is not pushed and you read this particular pin, which is configured as an input, you would read whether this push button is on or not. And when I push it down, this was grounded and we would read 0 volts, etc., etc. So you could connect a variety of tools and devices to the I/O port. And in fact, I/O ports is basically what gives the controller, what puts the word controller in microcontroller, because microcontrollers are usually used or employed to control something, whereas usually microprocessors, they use ports are actually data ports, and they're just for transferring information to and from memory, between the microprocessor and the memory, and you're just crunching numbers. Where here, I/O ports are mostly for controlling devices, and that's why they're called that, and that's why microcontrollers are called microcontrollers. Okay, now there are, in this example, I have 4 ports, and usually when 4 physical ports. When we talk about the physical port, and generally in conversation, I will write, port X, and I'm deliberately leaving this space so that we don't confuse it with the port register names. Okay, where X is either the letter A, B, C, D, etc., depending on how many ports you have. So, for example, if we're talking about port A, I'm going to say, port A this, port A that, or port B this, or port B that. But we're talking about generally about the port. Now, programming wise or software wise, the software perspective, the programmer's perspective of how to interact with each of these 4 ports, you always have 3 registers. Every port has associated with it 3 registers. Okay, first register is DDRx, again, where X is either A, B, C, D, etc. Every port has a port X, and every physical port has a PINx register. So these 3 registers are 8-bit wide. All of them are 8-bit wide, and together they are used to control, program, and configure any physical port X, emphasizing that space there. Okay, this register is called the data direction register. And the purpose of this register is to determine which pins are going to be configured as inputs and which pins are going to be configured as outputs. Okay, this, and when we do here, there's 8 bits, so each bit corresponds to each of these pins. Okay, so for the AVR, when you write a bit value of 0, that means you're configuring that pin as input, and when you write a 1, you're configuring it as output. Okay, once you have configured the port and its direction, then you can actually write out. So this is the data. Atmel calls it the data register, data port register, but let's just call it the output data. Sure, data output register. So whenever we write to this register, whatever you write to this register will appear on the actual pins. So if you write all 1s, we're going to get all highs, high voltage, as in high level, logic level. If we write all 0s, we're going to get all 0s here for all those pins that are configured only as outputs. Again, this only affects those pins that are configured as outputs. Whenever we have any pins configured as inputs and we want to read into, for example, we want to read this pin, but we have to read all 8 bits into a register. Okay, then we use the input port register. Okay, and basically try to use the mnemonic as a reminder that the I in pin stands for input register and the O in port stands for output. Okay, real quick, how would you configure a port? Well, basically you load any register. Usually I always go for R16, so load R16. Suppose I want to configure port A all outputs, every single one of these 8 bits, all outputs. So for port A, I would load all 1s, FF, and then move it from R16 onto the data direction register A. And there is no way for us to do this in 1 line of code. We have to do 2 lines. The first line is to load the immediate value onto a register, and the second is to move the value in that register to an IO register, and that is the DDRa. So these 2 lines configure port A. If I wanted to configure port B, all inputs, all of them. Okay, so this is all inputs and this is all outputs. Then once again, loading to a register the bit pattern to configure all inputs, that would be 0 0, and then output to DDRb the value in R16. So this would configure RB as all inputs. Suppose I wanted to configure, like I have here, 2 outputs, and the rest we could just have all inputs. Okay, so we do LDI R16. We have to determine the bit pattern for this. So remember, inputs is 0, so this would be 0 here, 4 bits at a time, so hexadecimal 0, and this is going to be 0 0, I mean 1 1 0 0, so that's 3. And then out DDRC R16. So these 2 lines of code would configure the port as I have here in the picture. Now let's talk about how to actually write to the port. If I want to write, let's start with you know, this port A. If I wanted to write all ones to the output port, excuse me, all we have to do is now LDI R16 FF, and then output to port A the value on R16. And again, we need minimum 2 lines, one to load the value we want to output, and then to actually output that value. So after this, all of these would be ones. Okay, so we use the output and the port name. Then suppose this port here, I want to read all of these 8 bits and put them into some register. Let's say R16. And to read it, you would simply do input into R16 pen B, not port B. This students always make mistakes. They will put port B when what you want to do is do pen B, right? And this would read all these 8 bits into R16, and then you could do, you could process the data in some way, etc., etc. So DDR registers when configuring. So this is where you always configuring the I/O port. You must never forget to configure the I/O ports before you actually interact with them in your program code. Okay, this is a mistake to interact with it without configuring. Another point that many students tend to make. After you have configured the registers, then you are free to, write data to it. All right, this is how you write it. And how do you read data from any port? Just give the port, and all 8 bits are read into the register. Now, if I were to read port C, okay, let's consider that scenario. Let me go ahead and copy this. Let me copy that and move on to a new window here, and I'll paste. That did not work. Oh, let me go back. I did not do that right. I need to copy merge, and then paste. There we go. Place that image up there. All right, make sure that I'm not messing with it. Okay, now if I wanted to read port C, which has a mixture of some of the pins that are being outputs and most of the pins are inputs, you can still read it. What you have to do is basically in R16 the value in pin C. Again, even though we have outputs and inputs, I only want to write, you read still via the pin C name, the pin name of the register. And then what's going to happen is that all of the 8 bits are going to be set. Alright, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Oops, 7. And this is R16. And what's going to happen is that we're going to get the current value that is for these 2 in the output. So this is going to be the value for the output, value for the output. So if you had that high, if you have these 2 on, then you're going to read 1 1 because you're reading what the output is set to. But for the rest of the registers, you would actually read whatever is on the inputs. Alright, so that means we need a way to ignore this. Let's say I'm only interested in this pin because this is the only pin I have something actually connected to, right? I need this and ignore all the rest. Okay, so to do that, the first step is of course to read it. But then what we could do is that we could actually use a mask to actually only allow this bit to come through and then set all the others to 0, right? So for example, I can have a mask where I set this to 0, 0, 1, 0, 0, 0, 0, 0, and when I do the bitwise AND operation between these two, then all of the bits are going to be 0, and then this is going to give me the bit value of whatever this guy is. Okay, so a good way to do this is that you would use the AND I instruction. In fact, let me make sure that we have such an instruction. If we while we're talking about this, you always want to have the instruction set manual handy. This is available at Blackboard, or you can just search for it in Google and get it. But I'm interested in the AND I instruction. There's an immediate AND I instruction, and the format, the syntax, basically means you have a register and you have a constant, which is a value between 0 and 255, and these must be a register between 16 and 31. Okay, and all that does is that it multiplies the 2, essentially. So I can say AND I R16 with the value, so this bit pattern is going to be 0, 4 in hex. And so after this line is executed, then I only have the input bit that matters, and then the whole register is going to be 0 or non-zero. And then you could do another test. You could compare it to see if it's 0 or non-zero using, for example, the CPI instruction, and then you could do something or not do something. So that's how you read, that's how you write. And again, same deal for writing. How would you write to a port that when you need to write all 8 bits at once? Okay, that's important. This is a key distinction. When we're writing all 8 bits at once with the in or out instruction, or with the out instruction, right? How will we write these two that are the only two as outputs but ignore the rest? We want to make sure we don't do that, affect the rest. So you would set the bit pattern and just make sure that the remaining of all the registers are all zeros. Okay, so if you wanted to turn them both on, then I would say LDI R16 03, so that I have 1 1 and the rest zeros, and then out port C R16. Notice now I'm using the port CB because I want to output, right? And here we use PIN because I was reading, and this is masking. This process of taking a bit pattern and using it to ignore and set all the others to 0 and only let a few select bits come through, this is called masking, bit masking. This is very important. Do that a lot in low-level programming. Okay, so that's how you actually manipulate a port, all 8 bits at once, that has a mixture between inputs and outputs, as opposed to certain ports that you will write all of them outputs, and certain ports where it'll be all of them inputs. Okay, but it still works out. All right, now we were talking about the thing about the in and the out instruction is that they write or read all 8 bits at once. Actually, we were just going to talk about writing. When we write, you use the out instruction, it writes all 8 bits at once. But if I'm going to do things like this, where I'm going to just mix some devices that some of them are outputs and some of them are inputs, I don't want to have to create a bit mask or I just want to go directly to the bit at the pin level. I want to just turn that one bit on or off without doing anything fancy. How do I do that? Well, there's actually 2 instructions to do that. Okay, these are single bit level instructions, and the 2 instructions you want to memorize in addition to in and out are the CBI and the SBI for clear bit, set bit. Okay, let's look at the data sheet. datasheet. Okay, and let's find CBI. If we can find it here somewhere, and I remember how to read alphabetical order. Clear bit in I/O. The syntax: you specify an address for the I/O register, which just uses the names that come from the include file. So port A, port B, port C, and then the bit number between 0 and 7. So if I want to turn, so I showed an example here. These two lines, my goal was to turn these 2 bits on, right? But I had to write all 8 bits. If I want to do the same as I did here in these 2 lines, I can actually just say set the bit in port C bit 0, and then set the bit in port C bit 1. So these instructions now allow me to individually turn this one line on and then individually turn this one line on, instead of writing an 8-bit value to achieve the same goal. Okay, so this is usually safer. You always want to, unless you really need to write all 8 bits, then you use the out instruction. But when you need to manipulate individual single bits, and you do that a lot in low-level programming, you want to use the SBI and CBI. And then suppose I add some delay. There's a delay in here. Maybe you wrote it as a procedure, and sometime later you want to turn that LED off. So once again, now we use CBI port C bit 0, and that will turn that bit off, etc., etc. SBI, CBI. Last thing you will want to know how to do is how to test a bit to check if it's set or clear, then do something or not do something if it's set or clear. So this is like a conditional branching in a way. Okay, so let's go ahead and move on to a new page. Let's go to page 3. Let's see if I can still paste it. Yep, I can still paste it. And let me make sure I don't overwrite it. Excuse me. Okay, conditional. So there's 2 instructions for testing whether a bit is set or clear, and then do something or not do something based on whether that test passes or fails. And that is the SBIS instruction and SBIC instruction. This means skip next instruction if the bit is set, a bit of your choosing in the I/O register. The bit in I/O register is set, okay, and skip the next instruction if the bit in the I/O register is cleared. Okay, so basically it works like this. Suppose that I have a loop, right, and I want to turn this light on whenever I push this switch. Okay, so I'm constantly reading the switch, and when the switch gets when the switch is 0, because this is active low, okay, so 0 means I pushed it, and 1 is going to read high when it's not pushed, or depressed, however you want to say it. And then based on that, I want to turn it on. So what you would do is I would first read, let's look at what that code would look like. I would read the switch. Actually, I don't need to read anything. I use the so I want to turn the light on if the switch is 0, and I want to not do anything if it's 1. So I want to skip the next instruction. So I'm going to say skip the next instruction if the bit is set on pin C. Again, I'm reading input bits, not output pins. Bit 0, 1, 2. Okay, so that means when this is pushed, this test will pass. So therefore the next instruction will not be skipped, and that might be a procedure to say turn LED on. Or alternatively, since we can do that particular task with 1 line of code, maybe I can just say SBI port C bit 0. Okay. So if you have many tasks, because we can only skip over only one instruction, only one line of code, if you have multiple lines of code that you want to skip, then you have to turn this into a procedure so that you can just use the call instruction. Okay, but in the case where we can achieve what we want to do in just one line of code, like in this case we can, then instead we will have this line of code here, and then you have more lines of codes here, right? So here the skip will either skip it or not skip it and do that. So this is how the SBIS and the SBIC does the same thing, but now it checks to see if it will skip it if it's clear. And these tests operate only on I/O registers, not on ordinary general registers, on I/O registers. So all the ports, you could test it on DDR registers, and you could actually test it on output registers to see what the current level is that you had set previously. Things like that. So these are conditional. You want to be aware these are conditional tests. And there are actually some laboratory exercises that this will come very handy. Okay, if you did not have this, then what you would have to do is that you would have to read the port into a general purpose register like R16. Then you would have to use bit masking like we did here. Okay, bit masking like we did here, and then after that we would have to check whether, you know, maybe use the CPI instruction to determine whether the bit is 0 or not 0, whether the register is 0 or not 0, and then act accordingly. But the SBIS and SBIC instructions allows us to do that more compactly. So you wanna again be mindful of those two instructions. Okay, now, so that's the essence, and those are the basics for that. Let's just look at this and actually watch it happen when we write some code. So let's go ahead and start a new solution. So I'm going to do this the way that we have to do this in lab, the way that I have shown our students we expect them to do. So again, reminder, if you are someone else who's just watching this video and you ask yourself why are they doing it that way, well, let's explain them some other videos. Okay, so we start by always making a blank solution. So I'm going to say IO tutorial underscore solution. We have an empty solution. Then we come here, not here, here, right click, add new project, and again I have my simulation templates and target templates as I had explained in a previous video. So we're going to simulate, I want to do simulator. Okay, IO tutorial simulator. And to be comprehensive, so that our students make sure they make a habit out of this, we're going to add the target. So target IO tutorial underscore target to differentiate the simulator from the target. Then we go back to our simulator code, and please don't forget to always fill up the info header. Alright, let's go ahead and let's pretend that we are on the blue board. Actually, on the blue board, my students know what the blue board is. This is our development kit. On the blue board, see if I have an empty window here. And yes, okay. On the blue board, we're actually using the AT90 or AT90 USB 1286, and there's another port called port E. That port is attached to a series of dip switches. Okay, and there's 8 dip switches, blah blah blah. Okay, you have the off position and you have the on position, and these are active low. So that means 0 means the switch is in the on position, and 1 means the switch is in the off position. Okay, so I want to read it via port E. So for our demonstration, let's configure port E. So I go to start code here, Remember, never forget, first order of the business, configure all I/O ports. Excuse me. Let's start with port E. Configure port E. So I want to configure port E all inputs because I want to read all the dip switches. So I'm going to say LDI R1600. And then output, do you remember what register? I would say pin E. However, because we have these equates here for reasons that are also explained in another video, I'm going to use the equate constant instead of the actual name, because I'm simulating on the Atmel 324P, and the 324P does not have a port E. So we use these equates to trick and redirect our code to a different register. Okay, port E, pin E R16. So this will configure port E as inputs. Now let's go ahead and configure, let's suppose, port C. Okay, so going back here on the blue board, actually it turns out that port C is connected to a series of bar. So ignore this. Port C on the blue board is connected to a series of bar graph LEDs. Blah blah blah. So once again, the bar graph LEDs are active low on the blue board, so that means a 0 will turn the corresponding LED on and a 1 will turn the corresponding LED off. Okay, so I want to set all that as outputs. LDI R16 FF output. Oh, I made a mistake. I'm setting the direction, configure direction. Okay, so the direction is DDRE. Okay, DDRC R16. Here I use the actual name. I'm only restricting port E to the underscore underscore notation because I have equates up here for that. Alright, then we can write to it. So let's go ahead and write some random value to port C. So suppose I do R16 and let's do 55 hex, which alternates 10 10 10 etc. And then output port C R16. Suppose I want to read a register. I want to read it. So read dip switches. So then I say in R16, in our case, underscore underscore pin E, because I have this equate here. A little cough. I'm very sorry about that. Let's stop here and let's just run it. So we build it. Right click, build. I do not hit build here because then it would do build both projects. Alright, and let's go ahead and start the debugger and break. Okay, I have my I/O window open, which I do by hitting the I/O icon. Registers, I open that by opening the registers icon, and the processor status I open by hitting the processor status icon. Okay, let's go ahead and step by hitting F10, step over. So F10, I'm going to load R16 with 0, F10, so R16 is 0, but it doesn't show me anything because the register was already 0. Then I'm going to write to DDRE, but in this program, DDRE points to DDRD. So then I come to DDRD, alright, and I'm going to write 00 to DDRE, or DDRD in this case, and because it was already 0, we don't see a change. Then I load R16 with FF, and there it is, FF, and I'm going to write to DDRC that value, so I point to port C. I can see DDRC right there, hit F10, and sure enough, now I have all outputs. Okay, now I'm going to write some random value to port C, so I load R16 with the value. There it is, 55. I output port C and notice 55. Okay, then I'm going to read pin E. Pin E points to port D, so let's go back to port D. We're going to be reading from this. Now, right here at this point, before I actually execute this instruction, I can simulate what my dip switches would look like. So for example, suppose I have all my dip switches in the off position. Remember, I said that this is active low. So if I have all my dip switches in the off position, then this dip switches would read all ones. So I can go back here and actually set my pin D to all ones by clicking with the bits with my mouse button, mouse icon. So, and then I execute the instruction, and sure enough, R16 is all ones because I have ones in here. But notice that it changes, which is why you have to do this right before you execute the input instruction, because it gets cleared. Okay, then we enter the infinite loop, and of course we're stuck in there forever, and that was explained in another video. Let's stop this and let's expand this. At this point right here, I have written 55. Let's do individual bit manipulation. So I can say clear CBI, clear bit on port C, bit 0, and then suppose there's some delay here, right? Maybe 1 second or something. And then after that, we SBI port C, bit 0 again. What would that look like? Control S, build it, start the simulator. Okay, hit F10, and you already saw what all of this looks like. So our focus will be on port C. So let's go back to port C, right? It's already configured as outputs. I can tell because these are all ones on the DDRc register. Then I load R16 with 55, and then up port C, and there it is. But now we're going to manipulate the bits individually. So I'm going to clear bit 0. So I hit F10, and notice that bit 0 got cleared. Notice that the outer is red to let you know that it changed. But the inside, whether it's filled or not, tells me what the state is, 0 or 1. It is 0. Okay, and then after that we had some delay. Let's suppose it took a second to execute, and then I'm going to set it again. So F10, and notice that the bit got set to 1. Okay, so this is a usefulness between CBI and SBI. And again, I want to read pin E, but in this program, pin E points to port D. So I hit port D, and suppose I have 4 switches off and 3 switches on. Remember, it's active low. That's why I'm saying the reverse. So I go ahead and execute that instruction, and sure enough, R16 has 0F. Okay, so you could test your code to see what would happen if I had this switch combination or that switch combination. You could test it yourself, even though nothing about this code is physically connected or knows about anything about dip switches, right? What matters is what the microcontroller sees at the port pins, and you could simulate that by clicking on the simulator. Now, for completeness sake, suppose that you want to download this to your upload this to the blue board itself. Remember, just to remind my students what they have to do, you copy everything from the orange down to the end of the program, copy, then we switch to the target, and again replace the orange and paste. Okay, but now the include file points to the right include. So previously it pointed to my simulator platform, and here I'm using the right device for the actual blue board, which is the AT90 USB 1286. Notice that this is why I use the equates, so that I don't have to go back individually wherever I use port E references and change them manually. The equates already take care of that for me. So here, port DDRe pointed to D because there is no physical port E. But here I have a port E, so my DDRe points to all my E registers without me having to change anything here, so that saves me time. So I should just be able to go right here and right click and build it, and I should have no problems, and this will generate the hex file, and I will use the flip utility to upload the hex file to my blueboard. Okay, and that's pretty much it. I'm going to skip showing you how to do SBIS and SBIC because I want you to try this on your own. Alright, and I also want to keep this video short. Okay, but remember that was for conditional execution of the following line of code. So I urge you to try some of these ideas on the simulator and try it out yourself. Alright, so that's pretty much it. I hope that this was useful in some way, and thank you for your time.